Hey y'all, welcome to Ms. Clark's chemistry class. In this lesson, I am going to be working through a practice test for stoichiometry and limiting an excess reactant. If you need help reviewing those topics, you have come to the right place. If you need a lesson on these topics, check out the link above. Start there first. This is a review. Guys, you cannot watch a review. You have to do a review. Work these problems. If you get stuck, let me explain you through it, and then try the next one. Pause it. Work through it as far as you can. Work through it all the way, and then let me work through it. Guys, if you are just watching, you are not utilizing this video to the fullest of its potential, and you are not working to your fullest potential. Go get your calculator, get your periodic table, get something to write with, and let's get started. Okay, number one. The reaction of sodium and iron 3 oxide is one in a series of reactions that inflates an automobile airbag. If 100 grams of sodium and 100 grams of iron 3 oxide are used in this reaction, determine the limiting reactant, the excess reactant, the mass of iron produced, and the mass of excess reactant after the reaction is complete. Now guys, I know I've said this once, I'm going to say it again. Every single question that you have to answer about limiting an excess reactant will take 2 problems at minimum. Anytime you're asked about the mass of excess, always a 3rd problem. Okay, let's get started at the beginning. You know that this is a limiting reactant problem. Well, this one says so. But if it didn't say so, you got 2 givens. That's how you know. First, you always start with a balanced chemical reaction. So if we go back at the beginning, it says the reaction of sodium and iron 3 oxide. Sodium and iron 3 oxide. This is a single replacement. Sodium is going to come and kick iron out. Iron is going to be all alone. Sodium is going to get with oxygen. Sodium is a 1, oxygen is a 2. So we get Na2O. Now we do need to balance this. Let's see where I would start. We've got 3 oxygens here. We've got 1 oxygen here. I would probably first start by putting a 3 here. That gives us 3 oxygens, but now we have 6 sodium. So I'm going to go ahead and put a 6 here. Now that didn't mess up anything. So the last element we need to look at is iron. And there are 2 irons in our reactants. So we need to put a 2 here. And again, that's not going to affect anything. Okay, so we have 6, 1, 2, 3 is our ratio. Now let's get ready to start our problem. I'm going to set up both problems at the same time. We've got 100 grams of sodium. That's our first given. Our second given is 100 grams of iron 3 oxide. If you were just looking for the limiting reactant and the excess reactant and that was it wouldn't matter which product you compare these 2 reactants to. But this problem specifically wants to know the mass of iron produced. So this is the product we need to compare everything to so we can compare apples to apples. So we need to convert 100 grams of sodium to grams of iron. And we need to convert 100 grams of iron 3 oxide also to grams of iron so we can see which one is going to run out first. Okay, so let's start our problem. We've got grams on top. We need to put grams on bottom. That's grams of sodium. That's going to be equal to 1 mole because this is going to be the molar mass still of sodium. What's on top comes on bottom. Moles of sodium on bottom. This is the first time we put mole on bottom, so we're going to put mole on top. This is our mole ratio. We're going to change to the element or the compound that we are solving for. We want to know about grams of iron. I'm going to go ahead and take it all the way to grams per iron because that's what our question wants to know. So again, what's on top comes on bottom. This is going to be a conversion factor, so I'm going to go ahead and put a 1 with mole. 1 mole of iron equals the molar mass of iron, grams of iron. We got to find these masses on the periodic table. Sodium, 22.99. Iron, 55.845. Now this mole ratio, mole over mole, we've got to look at our balanced chemical equation for that. Right here, 2 moles of iron, and sodium we have 6 moles. I'm going to go ahead and set up this second problem. Then we can just put it all in the calculator all at one time. Whatever is given, that's going to come on bottom, the unit. So we're going to put grams of Fe2O3. Grams means the mass, the molar mass. That's the mass of a mole. So we're going to put 1 mole on top. We got to go all the way to grams. So again, what's on top comes on bottom. This is the first time we're writing mole on bottom. So we've got to write mole on top, changing to our new compound. We still want to solve for iron. What's on top comes on bottom. 1 mole of iron. Again, the last step, we can put whatever we want on top. Whatever we're solving for grams. Molar mass of iron is still 55.845. There are 2 moles of iron, but this time we need to look at iron 3 oxide here. There's only 1 mole. Then we do have to add the molar mass of 2 irons and 3 oxygens. I feel like we have added up molar mass so many times that I can just put this into my calculator right quick and that there really is no need to explain what I'm doing. I really hope that that is the case. I'm getting 159.687. All of our units cancel. I'm going to put all of this into the calculator. Okay, so I'm working this top problem. Now, I'm not going to talk about how I'm typing this into the calculator because I find that confuses people sometimes. You could multiply across the top, multiply across the bottom, and then divide. Lots of different ways to put this into the calculator. Make sure you find a way that works best for you. Now, our beginning number was 100.0. That is 4 sig figs, so I'm going to use 4 sig figs. And I am getting, with 4 sig figs, oh no, that'll work, 80.97 grams of iron. Okay, let me put this next one in. Here I'm getting 69.94. Let's talk about what that means. If we have 100 grams of sodium, we could make 80.97 grams of iron. But we have this iron 3 oxide, and if we have 100 grams of that, we can only make 69.4 grams of iron. So if we were to go into the lab, grab our 100 grams of sodium, grab our 100 grams of iron 3 oxide, throw it together, make a reaction, we will only be able to make 69.94 grams of iron. Because as soon as iron 3 oxide runs out, the reaction will stop. So iron 3 oxide, that is our limiting reactant. How much product can be produced? That would be 69.94 grams of iron. We have not answered how much mass of excess reactant after the reaction is complete. That will require a third problem. Let me make some room. Okay, the third problem for the excess reactant is what normally messes people up. We know that the limiting reactant runs out. We're going to use all 100 grams of this. If the limiting reactant is iron 3 oxide, then the excess reactant has to be sodium because that's the only other reactant. So we know we have too much sodium. We are not going to use all 100 of this. And remember, with stoichiometry, we can compare any 2 parts of the reaction. We need to compare the thing we know we're going to use all of, that is our 100 grams of iron 3 oxide, and we need to compare that with sodium, the excess reactant, because we want to see how much did we use before the reaction stopped. Now, the third problem, no one likes working a third problem, but all of the molar masses are already added up for us. So when we bring down grams of Fe2O3, we already know that the molar mass is 159.687. Remember, that's the molar mass. What's on top comes on bottom. Moles of Fe2O3. We said that was 1. But we're going to compare this to moles of sodium. Moles of sodium, let's look back up to this problem. We had 6. We're going to go all the way to grams because we want to know the mass of the excess after we're done. What goes on top comes on bottom. 1 mole of sodium. 1 mole, because this is a conversion factor. We need the molar mass of sodium, 22.99. Okay, let's put this into the calculator. Okay, I am getting 86 point, I'm going to go with 4 sig figs because that's what everything has been, grams of sodium. Let's still talk about what this means. The reaction utilized all 100 grams of iron 3 oxide. When it utilized all 100 grams, it only needed 86.38 grams of sodium to do so. But remember, we started the problem out with 100 grams. So if we take that original 100 grams of sodium and we subtract it by how much sodium our reaction actually used, we will get how much excess is left over after the reaction is complete. Ooh, you know what? We are subtracting here. Let's think about sig fig rules. This number has 1 decimal place. This number has 2 decimal places. Remember, when you're adding and subtracting, you always use the least amount of decimal places. So in my answer, I'm only going to put 1 decimal place. So how much excess reactant is left? I'm getting 13.6 grams of sodium. Y'all, that was a little messy and kind of long. Let's go to the next one. Number 2. Photosynthesis in green plants uses carbon dioxide and water to produce glucose and oxygen. If a plant has 88 grams of carbon dioxide and 64 grams of water available for photosynthesis, write the balanced equation and determine the limiting reactant, excess reactant, mass in excess, and the mass of glucose produced. Pretty much all of the same things from the first question. Now, I'm going to go through this one a little bit quicker and not explain so much stuff. Okay, so he says photosynthesis uses carbon dioxide and water. So those are reactants. And it produces glucose and oxygen. Now this is the opposite of combustion. We need to balance this. I'm going to start with carbons. I have 6 carbons in my product, so I'm going to put a 6 here. Then if I go to my hydrogens, I got 12 hydrogens, so I'm going to put another 6 here. Now let's count up oxygens. Let's see, I've got 12 here. Got 6, that's 18, but there is 6 here. I don't want to put a number in front of glucose if I don't have to. So if I use 6 of them here, I really only have 12 left I need to account for. So I'm going to put a 6 here. We've got 2 givens. We've got 88 grams of carbon dioxide, and we've got 64 grams of water. This question did point us to a product, glucose. So we're going to solve both of these to glucose. If we weren't told to find how much product, we could choose oxygen if we wanted to. In fact, I would rather do oxygen because it's going to be easier to find its molar mass, but we can't because the problem asks for glucose. So I'm going to set my problem up and we're going to solve for grams of glucose for both of these problems. What's on top comes on bottom. I've got grams of carbon dioxide. That is the molar mass, 1 mole carbon dioxide. What's on top comes on bottom. This is the first time I'm putting mole on bottom. So we're going to put mole on top and change to the compound we want to know about. Y'all, who likes to write glucose? We bring mole on bottom, and that is the molar mass. So we need to add up the molar mass of 6 carbons, 12 hydrogens, 6 oxygens. Okay, the second problem. Again, we need to go all the way to glucose. What's on top comes on bottom, grams of water. That's the molar mass. So it's equal to 1 mole, of water, not mole. Here we go. What's on top comes on bottom, mole of water. First time mole comes on bottom, mole comes on top, and we change compounds. What's on top comes on bottom. This is going to be our conversion factor again, and that is equal to a mole. Molar mass of water, I happen to have that memorized from calculating hydrates so much, so I'm just going to put 18.015. If you have it memorized, just put it in there. I'm going to go ahead and find the molar mass of carbon dioxide, 44.009. Moles of glucose, there's only 1. Carbon dioxide, there are 6. Ooh, glucose. Let's add up glucose. And I'm getting 180.156. I'm going to put that in both places. I'm going to go ahead and finish up down here before I put this in the calculator. I am right here, moles of glucose. Remember, there's just 1. And then moles of water, there are 6. Okay, let's put this in the calculator. I'm going to do the top problem first. I'm getting 60, we need 3 sig figs, 60.0 grams of glucose. And then the second problem, and I am getting 106. Oh, that's 3 sig figs, so actually that's going to be 107 grams of glucose. Okay, so remember, we've got to look at which one produces the least amount because that tells us which one runs out first. So carbon dioxide is going to be our limiting reactant because it produced the least amount of glucose, meaning water is going to be our excess reactant. Here, I'm going to make a list over here to the side. Our limiting reactant was carbon dioxide. Our excess reactant is water. Products produced, that would be glucose produced. That is 60.0 grams. The last problem we have to work is the mass of excess. That is our third problem. Y'all pause. Figure out that third problem before you watch me do it. Don't just listen to me. Okay, remember, your given is going to be the thing you run out first, the limiting reactant, because we use all of it. We know we use all 88 grams, So that is driving our reaction. But how much water did we use? We were given 64 grams, but we did not use all of it. Let's see how much we used. So we're going to start with 88 grams of carbon dioxide. We're going to bring that down, grams of carbon dioxide. We've already added that up, so I'm going to go ahead and put it in, 44.009. That is the molar mass, so that is equal to a mole of carbon dioxide. What's on top comes on bottom. Moles of carbon dioxide comparing to moles of water. Remember, we want to see how much water we used. Bring that down, moles of water, the molar mass of water. Let's fill in our mole ratio. We had 6 moles of water. We had 6 moles of carbon dioxide. Those are going to cancel out. Okay, let's put this in the calculator. I see that we only used 36.0 grams of water. And since the question asks what is the mass in excess, so how much do we have left over, we were given 64 grams of water. We used 36 grams of water. So we only have 28 grams left. Next question. Number 3. Determine the number of moles of iron 2 hydroxide produced if 5 moles of iron and 8 moles of nickel oxide hydroxide react. Y'all, I'm going to be real honest. I had to look up what this compound was, and it is called nickel oxide hydroxide. Okay, now I wanted to make sure and show you a problem like this because it requires way less work, and that normally freaks y'all out. Now, this is definitely a limiting reactant problem because we have 2 givens. 2 givens, especially when those 2 givens are reactants. We have 5 moles of iron and we have 8 moles of this nickel oxide hydroxide. Definitely going to be a limiting reactant problem, but it is just dealing with moles. So this is going to be a very short problem. Now let's go ahead and pay attention that it says determine the number of moles of iron 2 hydroxide. This is iron 2 hydroxide right here. This is the product we need to be comparing things to, but it did ask us just for moles. So we're going to start our problem with 5 moles of iron, and then we have 8 moles of nickel oxide hydroxide. And we're only asked about moles of iron 2 hydroxide. So let's keep that in mind. What's on top comes on bottom, moles of iron. The first time you put mole on bottom, you put mole on top. We want to know about iron 2 hydroxide, and that's what we want to know about, moles, equal sign. Because if we put an equal sign there, it'll tell us moles, because that's what's on top. What's on top comes on bottom, moles of nickel oxide hydroxide. First time we put mole on bottom, we put mole on top. We want to compare to the same product, iron 2 hydroxide. And since we're only looking for moles, we're going to stop. There is no reason to carry this problem further. So let's look at our balanced equation. We've got 1 mole of iron. We have 1 mole of iron 2 hydroxide. And we have 2 moles of nickel oxide hydroxide. So 5 times 1 divided by 1 is just 5. And 8 times 1 divided by 2 is just going to be 4. Now this problem asked us how much iron 2 hydroxide will be produced. And it always has to be the least amount. We will only produce 4 moles because the limiting reactant is nickel oxide hydroxide. That was pretty short, right? Y'all, I always throw one of these short ones into the test because I want you to have a little bit of a break. Make sure you realize that this problem is offering you a break. Zinc reacts with iodine in a synthesis reaction. Write the balanced chemical equation for the reaction. Determine the theoretical yield if a 125 gram sample of zinc was used in excess iodine. Determine percent yield if 515 grams of product are recovered. Y'all, this problem is just a stoichiometry problem, and we know that because there is only one given. And we also know that because it's telling us that one of the reactants is in excess. It says in excess iodine. That means our given information is the limiting reactant. So we don't have to figure that out. Now, when we first started working stoichiometry problems, we would see that in the directions, or we would see that in the question. It would tell us, you've got so much of this, and then this is in excess. Now we understand why. You can only determine the theoretical yield from the limiting reactant. We know zinc is going to be the limiting because iodine is in excess. Okay, zinc reacts with iodine. Remember, iodine is diatomic. Zinc is always a 2, and so we get ZnI2. Y'all, please realize this 2 and this 2 are not the same 2. This 2 is because iodine is diatomic. This 2 is because zinc is a +2, I is a -1. But we don't have to balance this equation because it is already balanced. Let's just go ahead and work this problem. We have 125 grams of zinc. We want to know about the zinc iodine. Now, we know we have to solve for grams because our actual yield is in grams. If your actual yield is in grams, then we've definitely got to have our theoretical yield in grams as well. And remember, the answer to this is just called the theoretical yield. So what's on top comes on bottom, grams of zinc. That's the molar mass, so that's 1 mole of zinc. Bring that down, mole of zinc. This is the first time we're putting mole on bottom. We're going to put mole on top, and we want to know about ZnI2. What's on top comes on bottom. I'm putting a 1 because this is a conversion factor, and we need to use grams, so we need to find the molar mass. All of these are 1, so I'm just going to go ahead and put those there. Zinc from the periodic table is just 65.38. And then if I add up 2 iodines and 1 zinc, I'm getting 319.188. Okay, put all this in the calculator. With 3 sig figs, I am getting 610. And to make that 3 sig figs, I'm going to put that decimal here. That would be grams of ZnI2. Remember, this is our theoretical yield. We want to determine the percent yield. Percent yield is our actual yield over our theoretical yield. Now that's going to give us a decimal, so we need to multiply by 100 to get a percent. Our actual yield will always be given in the problem, or you've done this in the lab, 505 grams. Our theoretical yield, this is the problem we just worked. So 515 divided by 610 times 100, and I am getting 84.4% yield. Question 5. Okay, question 5. When copper wire is placed in a silver nitrate solution, silver crystals in copper 2 nitrate solution form. Write the balanced equation for the reaction. If 25 grams of copper are used, determine the theoretical yield of silver. If 65 grams are actually recovered from the reaction, determine the percent yield of the reaction. This, again, is just a stoichiometry problem because we only have 1 given. This is our actual yield. We won't use that until the end. First, we have to write and balance this chemical reaction. So copper wire is in a silver nitrate solution. Remember, silver is a 1, nitrate's a 1. So copper is going to kick silver out. We know this reaction completes because silver crystals form. So silver gets kicked out, and we are forming copper 2 nitrate. Copper is a 2, nitrate is a 1, so we get CuNO3 2. We need to balance that. I'm going to put a 2 for 2 nitrates, 2 silvers. We're done. So we've got 1, 2, 2, 1 is our ratio. So our given, 25 grams of copper. And then let's go see what we're solving for. Determine the theoretical yield of silver. Duh, silver, that's what we're trying to get. So we're going to bring down grams of copper. That's the molar mass, so I'm going to equal that to 1 mole of copper. What's on top comes on bottom. Moles of copper. First time we put mole on bottom, we put mole on top and change to what we were looking for. We were looking for silver, and we want to know about grams of silver, so we got to keep going. 1 mole on bottom, grams of silver. Grams of silver on the periodic table is 107.868. Copper is 63.546. 2 moles of silver, 1 mole of copper. Let's put that in the calculator. With 3 sig figs, I am getting 84.9 grams of silver. Now remember, it did ask us for theoretical yield. This is the theoretical yield. But we're also asked to find percent yield. So actual, that's 65, divided by theoretical, that's 84.9, times 100 to get a percent. And I am getting 76.6% yield. Question 6. Ethanol is produced from the fermentation of sucrose in the presence of enzymes. And then here is this reaction. Determine the theoretical and percent yield of ethanol if 648 grams of sucrose undergoes fermentation and 349 grams of ethanol is obtained. Again, this is just a stoichiometry problem because we have one given, because this is our actual yield. So we need to solve for grams of ethanol because that is our actual yield. So we need to find our theoretical yield to match that. So we're going to start with 648 grams of sucrose. Y'all, I'm just going to write like sucrose like this. What's on top comes on bottom. Grams of sucrose. That is 1 mole of sucrose. What's on top comes on bottom. Moles of sucrose. We're going to change to moles of ethanol. I'm just going to write ETH. Moles of ethanol come down on bottom. That's 1 mole because this is now a conversion factor. Grams of ethanol. Ethanol had 4 moles. Sucrose only had 1 mole. Okay, let's add up sucrose's molar mass. That's 12 carbons, 22 hydrogens, and 11 oxygens. 342.297. And then ethanol, that's 2 carbons, 6 hydrogens. Do we see that? And only 1 oxygen. And I'm getting that to be 46.069. Let's put that in the calculator. I'm getting 349 with 3 sig figs of ethanol. Now that was one of the questions. That's our theoretical yield. We also need the percent yield. Our actual yield is 349. Oh, our theoretical yield is 349. That is a 100% yield, y'all. It don't get any better than that. One more question. Let's go. Lead 2 oxide is obtained by roasting lead 2 sulfide in air. Balance the equation and determine the theoretical yield of lead 2 oxide if 200 grams of lead 2 sulfide is heated. What is the percent yield if 170 grams of lead 2 oxide are produced? Let's balance this equation first. Okay, I'm going to show you what I always do. I am going to start by putting a 2 right here. The reason why is because I've got 2 oxygens on this side. And on this side, my oxygens are split apart. I have 2 here, but this 1 is always going to make it odd. So I'm going to make it even. So I'm going to put a 2 right here. That gives me 4 oxygens. So I'm going to put a 2 here. That also gives me 2 PBs. So I'm going to put a 2 here. Oh, dang. That gives me 2 sulfurs. So I need to put a 2 here. I've got to re-add up my oxygens. Are you noticing that? Now I have 2 oxygens here plus 4 oxygens here. I have 6 oxygens. Oops, not a 6, but a 3. Okay, here we go. Y'all, another stoichiometry problem. Again, one given. 200 grams of PBS. We are determining the theoretical yield of PBO. So that's where we're going. What's on top comes on bottom. Grams of PBS. That is equal to a mole. So 1 mole of PBS. What's on top comes on bottom. Mole. First time we put mole on bottom, we put mole on top. We're going to change to our new compound, which is lead 2 oxide. Bring that on bottom. 1 mole of lead 2 oxide. Mass. PBO. Okay. Moles of PBO, that's 2. Moles of PBS, still 2. Let's add these molar masses up. I'm getting 239.266 and 223.199. Okay, let's put this in the calculator. I am getting, with 3 sig figs, 187 grams of lead 2 oxide. Theoretical yield, but we need the percent yield. The actual, 170 divided by 187 times 100 to get a percent. And I am getting 90.9% yield. Okay, y'all, I hope that really helps. If you're working the problems with me, don't just watch me. You cannot watch science happen. You've got to do science. But until next time, bye, y'all.